There's a wonderful book called Normal Accidents by Charles Perrow. I don't know if anyone's ever read it. It's about how technological complexity introduces unquantifiable uncertainties into social and technical systems and leads to often things that can be disastrous, like nuclear plant accidents. And Normal Accidents starts to illustrate the concept. It starts with just a little scenario of someone who's got a job interview, and he or she is in a rush and anxious, and they knock over their coffee pot, and that delays them 15 minutes, so they're in a rush to get out of the house, and they realize they left their keys in the house, but they lock the door behind them, and they sort of go to get their emergency key, which is a redundant system, but it turns out they had lent it to a friend the week before, and they end up being very late to their interview and not looking very credible. So anyway, I guess that was my morning or something. Combined with, being a bobble-headed, overcommitted person in late middle age. So we're going to talk about an uncertainty in a way that's probably unfamiliar to most of you and may seem kind of goofy. And Vanessa said we'd tell you a little bit about the Consortium for Science Policy and Outcomes, and I'm not going to do that directly, but some of what we do will come out in Mahmud's part of the talk, where he'll sort of talk more operationally about the kinds of things we do. But what I want to suggest is that a lot of the ways we think about how to deal with uncertainty don't come to terms with the political essence of the concept. And so I'm going to discuss uncertainty in a way that I think is probably different from how most of you are used to thinking about it, but hopefully it will make some sense. Now I need some way to... I just look at... Okay, so let's have the first slide. So the first thing I want to do is introduce kind of what we call in academia a theoretical construct. But I think I think it provides some value in terms of understanding why we're talking about uncertainty in the way we are today, rather than the standard way of probabilities and models and error bars and such things. And the major point is that a lot of the sorts of problems that science is asked to take part in helping us understand how to solve difficult social problems, a lot of these sorts of problems are not the kinds of things that science is made to address. They're not situations where you can control, you can create controlled experiments where you can test hypotheses in settings that allow you to reproduce your results. They're situations where systems, as you all know, are non-deterministic, complex, open, and equally important, where there's contested values at stake as well as the difficulty of the science itself, where there's often urgency and need to make decisions, or at least a need to get information out there that decision makers can act on. And so in the terms of two philosophers, Jerry Revets and Silvio Funtowitz, they emphasize that this isn't the way we normally think about science, even though we often talk about science as if it's the same in these situations, but it's not. They call it post-normal science. The idea there was to contrast it with, for those of you who have read Thomas Kuhn's wonderful book, The Structure of Scientific Revolution, sort of normal science is what we as scientists normally do. But they're talking about, and they call our attention to the fact that a lot of science in these contested political complex problem environments is something different, which they call post-normal science. Uncertain facts, disputed values, high stakes, decisions urgent. And that's where a lot of us are in our work. And uncertainty is something different in that domain than when we're just doing science as scientists. Next, please. So I'm going to give you run through a couple of examples rather quickly, but to try to illustrate this. And the first, so I'm a geologist by training, even though I've been a policy wonk for more than 20 years. So two of my three examples will be rooted in earth sciences, where I'm sort of more intellectually comfortable. But so the first example has to do with the behavior of the San Andreas Fault. And this is the famous 1906 rupture of the fault north of San Francisco. And of course, the behavior of the fault has been the object of lots of scientific research over the years, including in the late 1980s, an effort to actually predict failure on the San Andreas along a particular segment of the fault called the Parkfield segment. And I'm not going to tell you where the Parkfield segment is. I'm going to ask you to guess later on. So if If anyone knows, please don't give away the answer. But the point is that scientists working along this particular segment of the San Andreas discovered a remarkable periodicity in ruptures of the fault over a period of more than a century, where it was rupturing about every 22 years. And they developed a very nice model that explained strain buildup and rupture, and predicted with 95% certainty that there would be another rupture during the period 1988 to 1993. Okay, and the point I want to make is it's not just that the scientists did this work and made this prediction, but this was very high-profile science. Okay, it was published in Science magazine, so it was peer-reviewed, but it was also reviewed by 2 expert panels, one a California earthquake prediction panel and then a national earthquake prediction panel, both of whom also endorsed the prediction. So 95% certain that we're going to have a rupture on the San Andreas. These are moderate-sized earthquakes, 6.0, so it can cause some damage but not devastating, over this 5-year period. And the 5 years came and went, and the earthquake didn't happen. And also a lot of resources were put around monitoring the earthquake so that it could be actually observed very, very closely as it occurred. It didn't happen in that 5 years. I think it happened maybe 2004. There was a rupture there, even smaller though than had been expected. So way outside the statistical expectations. So here's the question that interests me. What does that 95% certainty mean? And does the fact that Parkville didn't behave as predicted simply mean that, well, 95% certain still means there's a 5% chance that it wouldn't happen, and so the scientists were unlucky? Or does it mean there's something else going on? So can I have the next slide? So where does the uncertainty come from is what I want to ask. And what I want to suggest is it doesn't actually come from nature. It's not something that's given to us by our understanding, our kind of unmediated wrestling with nature through scientific processes. There's an additional element, and that's a political or social element. Next, please. So here's the city of San Francisco, where the San Andreas Fault crosses and threatens the city in terms of its future well-being with a possible significant earthquake, and kind of another slide. And here's an area south of San Francisco, a rural area where the San Andreas Fault also crosses through and similarly has a high probability of seismic risk. So let me ask you, do you think the Parkville segment goes through San Francisco or goes through this rural area? That's your test. Why?
Easy to study.
Well, partly easy to study, and what else?
Highly visible.
No, this is true on the science end. What about on the political or social end? Who cares if there's a rupture of the fault in this Parkville segment? A couple of farms will get shaken. A couple of cows will get upset. Okay. Now, immediately after the failure of the experiment, that is, immediately after it was clear that the earthquake wasn't going to take place within the 95%, the stipulated time that was given a 95% probability, what happened? Scientists go back. What's wrong? Well, they quickly found what was wrong. There were a few other events that hadn't been that had actually occurred and didn't fit the model and hadn't been included in it. This wasn't intentional. This is science. We all have to decide what data we want to use, et cetera, et cetera. But the point is that it's actually unimaginable that this would have happened had the fault run through San Francisco, because the stakes are enormously higher. Okay? So the obstacles to making a 95% prediction of an earthquake that would be a hugely socially destabilizing force, I would submit, are much, much higher. The scrutiny would have been higher. More scientists would have been drawn into the science. More institutions would have been drawn into the process of evaluating the science. It's counterfactual, I acknowledge, but nonetheless, I think it kind of it comports with our intuition about how these sorts of things work.